Section 2.6, Two Quantitative Variables, Linear Regression, Video 6. As with correlation, regression comes with some cautions. We've already talked about some of these. For example, number 1, do not use a regression to make predictions about explanatory values outside the range of observed explanatory values. In the margin of victory versus approval rating scatter plot, our approval ratings that we observed were between 30 and 70, so we shouldn't use the equation to make predictions for approval ratings that are less than 30 or greater than 70. Here's another real quick example. Although I don't have the data, I'm pretty sure that the following association would be negative. Let's say that on the horizontal axis we are measuring the year, and on the vertical axis we're going to record the record time for the 100-meter dash. I think it's safe to say that over the course of time this record has been broken over and over and over again. So in the past the record may have been up there, and then as the years go by people run faster and faster and faster. Because the times are decreasing as the years increase, this would have a negative association, which means that its line of best fit would be going downward. Well, if a line's going downward, it's eventually going to hit the horizontal axis. And what happens on the horizontal axis? The value of the response variable is 0. So if we were to try to use this to make predictions beyond what we observed, we would get a meaningless result, such as in the year 2050, we expect the record time for the 100-meter dash to be -1 second. That doesn't even make sense. So don't use a regression to make predictions about explanatory values that were outside of the range of the observed explanatory values that were used to create the regression in the first place. Number 2, plot the data. Why? Because a linear regression should be used for linear data. If you plot data and it's a parabola or something curvy, using a linear regression would be the wrong regression to use. I mentioned previously, I think it was in the module, but it might have been in the last set of videos, that there are other types of regressions. There are quadratic regressions. There are exponential regressions. There are reciprocal regressions. There are sinusoidal regressions. But we're only going to worry about the easy one, linear ones. If your data is not linear, you should not be using a regression line to describe it or make predictions. And as usual, outliers tend to mess things up. And again, I can't remember if it was in the module where I showed the 2 scatter plots for the calories consumed and alcoholic beverages consumed. If you have your textbook, I would flip back to the page where those scatter plots are. I'm getting there. They are on page 114. And I know you really can't see the 2 scatter plots on the bottom of this page, but one of them has an outlier way up in the upper right-hand corner. And in order to see that outlier, you have to zoom out really far from the scatter plot, and the rest of the points look like they're sitting on a line. But if you remove that one point and zoom in on the rest of the scatter plot, you'll see that the points actually weren't very linear at all. Outliers force you to zoom out and not get a true perspective of whether or not a data set is linear. So if you see outliers, be aware of them, and sometimes you should just disregard them and consider the rest of the scatter plot. So be careful when you're using a linear regression. Don't use it when you shouldn't. Don't use it when you shouldn't. And if there are outliers, proceed with caution.